Take a moment and observe your surroundings. Illumination is absolutely everywhere, isn't it? Your perception of the world exists because electromagnetic radiation enters your visual organs. Straightforward enough. But here's something fascinating to consider. At this very instant, radiation from every single object around you is propagating in countless directions. The moment you observe something, electromagnetic waves from that particular object arrive at your eyes. Simultaneously, though, radiation from your own body is traveling toward that same object. Electromagnetic radiation crisscrosses through space continuously, waves overlapping and intersecting, traversing identical regions. How is this even possible? How can countless billions of electromagnetic rays propagate in all directions without creating complete disorder? How do you perceive a sharp, clear image when such overwhelming chaos surrounds you? And remember, that's merely the visible spectrum. At this precise moment, radio transmissions are passing directly through your location. Television transmissions, thermal radiation emanating from your physical form, radar signals from aircraft, cosmic X-rays, all traveling simultaneously through identical space, through your very body. Every single one of these represents the same fundamental phenomenon as light, distinguished only by wavelength differences. So let me ask you this. What exactly is light? Not the simplified explanation you encountered in your education. That version is incomplete, perhaps even misleading in significant ways. The genuine answer, what electromagnetic radiation truly is, and how it propagates from location to location, is remarkably strange, profoundly unlike anything you encounter daily. So much so that when comprehension finally arrives, your entire perception of reality transforms. Let me demonstrate this for you. Picture yourself seated beside a swimming pool. Various people are diving into the water. Splash after splash after splash. Waves radiate across the water's surface, ripples intersecting with ripples, absolute chaos unfolding. Now consider this. Imagine an intelligent insect positioned in the pool's corner, simply resting there, sensing the water bumping rhythmically against its body. These waves arrive from varied directions, different frequencies, different intensities. Is it conceivable that this insect, merely by sensing these wave patterns, could reconstruct what's happening throughout the pool? Could it determine who entered the water, where they entered, the timing of each entry, everything occurring across the entire pool? It sounds utterly impossible, yet remarkably, yes, theoretically, all that information exists within the waves. That's precisely what you're doing at this very moment. When you observe anything, the electromagnetic radiation reaching your visual organ consists of waves, remarkably similar to that pool, except propagating in 3 dimensions rather than 2. Dimensions, waves propagating in every conceivable direction, crisscrossing, overlapping, creating complete disorder. And your eye. It's merely a 1/8 inch aperture, a minuscule detector, exceptionally sensitive to waves arriving from specific directions, less sensitive to waves from your peripheral vision. Unless you rotate your eyeball to reposition that aperture, from this chaotic mess of waves, you successfully extract a coherent image of reality. You determine what you're observing from a distance. And here's the truly astonishing part. When you're observing me standing here, someone positioned to your left can simultaneously see someone positioned to your right. Electromagnetic radiation travels this direction. Electromagnetic radiation travels that direction. Waves in every conceivable direction. An elaborate network. It's nothing like arrows piercing through one another. It's something oscillating the electric field, similar to water height fluctuating up and down. Some quantity vibrating everywhere simultaneously. The combination of movements so intricate and complex that the resulting effect produces an influence allowing you to see me at the same moment completely unaffected by the influences allowing that other individual to see someone else entirely. There exists this tremendous disorder of waves throughout all space. Electromagnetic radiation bouncing around your environment, traveling from one object to another. Most objects lack 1/8 inch apertures to detect it, so they remain uninterested. But the radiation is present regardless, reflecting off this object, reflecting off that object, all occurring simultaneously. And yet we manage to sort it all out with this remarkable little instrument we call an eye, navigating this invisible ocean. But remember, that's merely visible spectrum radiation, the waves your visual organ can detect. Think about those pool waves once more. Some waves are large, others are small, some are slow, elongated swells. Others are quick, abbreviated ripples. Your hypothetical insect might exclusively study waves between particular sizes. It turns out the eye exclusively utilizes waves between certain wavelengths too. Except those wavelengths are incredibly tiny, approximately 1/100,000th of an inch. What about the extended waves, though? These slower, longer swells, those represent thermal energy. We sense them through touch, infrared radiation. Our visual organs cannot perceive them, but their presence is undeniable. Pit vipers, those desert snakes, possess specialized organs capable of perceiving these extended waves. They can detect mice radiating body warmth, see them in absolute darkness by detecting infrared radiation. We lack this capability. Our visual organs weren't constructed for it. And the waves extend even longer, much, much longer. Radio waves exist, identical to light fundamentally. Precisely the same category of wave, just substantially longer, vastly longer. Which means, at this very instant, sitting exactly where you are, there's not merely the visible radiation enabling you to see this page. There's also information from broadcasting stations, Moscow radio, transmitting at this precise moment. Signals originating from Peru, radar from an aircraft calculating its position, all passing through this location right now. Plus X-rays, cosmic radiation, all identical categories of waves. Precisely the same phenomenon, just abbreviated, faster oscillations. It's genuinely all present. You're skeptical? Obtain a piece of wire connected to a device, a radio receiver. The electrons within the wire get pushed backward and forward by the electric field oscillating at precisely the correct speed for certain extended waves. Adjust the controls to achieve the oscillation just right, and you hear Moscow radio broadcasting. Then you understand it was present all along. How else could it arrive there? It was present continuously. You only become aware of it when you activate the radio receiver. All these phenomena passing through the room simultaneously. Everyone understands this intellectually, but you must pause and contemplate it to genuinely experience the pleasure, the inconceivable nature of reality itself. For multiple centuries, people debated about what electromagnetic radiation truly is. Newton claimed light consisted of particles, tiny bullets propelling through space, corpuscles, his term for them. That's the reason light travels in straight trajectories. That's why you cannot bend it around obstacles. Huygens held a different view. Light is a wave phenomenon, he insisted, similar to sound, similar to ripples in water. Waves propagate outward. Waves interfere with one another. They couldn't both be correct, could they? The debate continued for 200 years. Then experiments arrived that appeared to resolve it. Direct light through two narrow openings. What do you observe on a screen positioned behind them? If light consisted of particles, you'd observe two luminous strips, bullets passing through openings. But that's not the result. You observe a pattern, luminous bands and dark bands, interference, precisely what waves produce when they overlap. When two wave crests coincide, you get brightness. When a crest encounters a trough, they cancel, producing darkness. Light must be a wave phenomenon. Debate concluded. Except subsequently someone constructed a detector sensitive enough to capture individual photons. And what occurred? Click, click, click. Individual arrivals, resembling bullets, resembling particles. But wait, transmit them through one at a time. Surely a single particle cannot interfere with itself. It does exactly that, one photon at a time, and the interference pattern accumulates. Each photon appears to pass through both openings simultaneously, like a wave. So tell me, which is it? Wave or particle phenomenon? Here's something most people won't reveal to you. It's neither option. Light is not a wave. Light is not a particle. Light is light. We lack a word for it, because we lack anything resembling it in everyday experience. We attempt to describe it using familiar concepts, waves, particles. But those are merely approximations, supports for our imagination. The reality is more strange. Photons are genuine, individual quanta of electromagnetic radiation. You can count them individually. They make detectors click audibly, but they don't behave like tiny bullets. They behave according to quantum mechanical principles, which means they explore all conceivable paths simultaneously, like waves spreading outward. When you attempt to observe which opening a photon passes through, The interference pattern vanishes. The wave behavior disappears. You get particle behavior instead. Not because photons are sometimes waves and sometimes particles, but because asking which opening is asking a particle type question. And when you ask particle type questions, you receive particle type answers. The photon doesn't choose to be a wave or a particle. It's always itself a quantum object. What changes is how we decide to measure it. This isn't philosophical speculation. This is how nature genuinely operates. And it's far more strange than anyone ever imagined. So if electromagnetic radiation isn't particles flying in straight trajectories, why does it go straight? Here's where things become beautiful. Light selects the path of shortest duration. That's Fermat's principle, discovered during the 1650s. Not shortest distance, shortest duration. Light travels slower through glass than through air. So when light goes from air through glass back to air, it doesn't take the straight line. It bends at the interfaces, takes a path that's longer in distance, but shorter in time. That's refraction. That's why objects appear displaced when you view them through water. The light bent, selected the fastest route. This explains lenses. Want to focus light from a distant source? You need all the light arriving to reach one location simultaneously. Light naturally travels in straight lines through air, taking the shortest time path. But different rays from the source travel different distances to reach the focus. The ones passing through the center travel less distance than the ones passing through the edges. It'll select the fastest route unless we equalize all the times. That's the secret revealed. A lens equalizes all path durations. Here's the method. Glass decelerates light. So, if we select a ray that would naturally traverse a longer distance, we can insert some glass to decelerate it. Compensate for the extra distance by adding extra delay. We obtain a glass piece thicker in the center, thinner at the periphery. All paths straight through the center, angled through the sides, require the same duration. That's a lens, a device that equalizes travel durations. The same principle functions for mirrors. Want to collect starlight from billions of miles distant and bring it to a focus? Create a curved mirror. Shape it so that light striking anywhere on the mirror requires the same total duration to reach the focal point. That shape is a parabola. The 200-inch Palomar telescope employs precisely this principle. All optical instruments, telescopes, microscopes, eyeglasses, function by manipulating travel durations, making some paths faster, some slower to control where electromagnetic radiation goes. But here's the most profound question. How does light understand which path requires the least duration? Does it somehow sense the adjacent paths, compare them against each other, select the optimal one? The answer is affirmative. In a manner of speaking, that's the feature you cannot explain with straight lines and rays. That's where wavelength enters the picture. The wavelength informs us approximately how far away the light must verify other paths. It's difficult to demonstrate with visible radiation because wavelengths are remarkably short. But with radio waves, say 3 centimeter waves, the effect is more substantial. Position a source, a detector, and a slit between them. Radio waves propagate from source to detector through the slit. Fine. Make the slit more narrow. Still functions. Now, relocate the detector to the side. The waves won't propagate there through a wide slit. Why not? Because they're verifying several paths nearby, and those paths correspond to different durations. The waves interfere with themselves, cancel out, but close the slit down to an extremely narrow crack. Now there's only one path available. The waves have nothing to compare against, so they select it. With a narrow slit, more radiation reaches the sideways detector than with a wide slit. You can perform this with visible light, too. Here's the method. Locate a small luminous light, a distant street light, or sun reflection in a car bumper. Hold 2 fingers in front of one eye. Observe. Through the crack, squeeze your fingers together gently. The light, which was a small dot, becomes elongated, stretches into a line, and if you observe carefully, you'll see fringes, bands along the edges, colors. Why does this happen? The fingers are extremely close together. The light spreads out at an angle. It enters your eye from several directions instead of one. This is electromagnetic radiation, not propagating in straight trajectories, light verifying nearby paths, light behaving like a wave phenomenon. So, what's genuinely happening? What is electromagnetic radiation really doing? Here's the modern understanding, the quantum mechanical picture. Light consists of photons, genuine particles. Detectors click when they arrive. The brightness of illumination is proportional to the quantity of photons per second. But photons don't travel like bullets. When a photon propagates from point A to point B, it doesn't select one path. It explores all conceivable paths simultaneously. For each path, you draw a tiny arrow, a complex number. The angle of that arrow is proportional to the duration that path requires. The faster the light oscillates, the more the angle rotates. That's frequency. Different paths require different durations, so the arrows point in different directions. Now add up all the arrows, all conceivable paths. The probability that the photon arrives is proportional to the square of the length of the sum. Here's what occurs near the path of least duration. The duration doesn't change substantially, as you vary the path slightly. So arrows for adjacent paths all point in roughly the same direction. They add up, reinforce each other. Far from the path of least duration, small changes in path produce substantial changes in duration. The arrows point everywhere. They cancel out, form a tight spiral. Almost all the probability originates from paths near the minimum duration. That's the reason light follows the path of least duration. Not because it exclusively takes that path, but because all the paths distant from it cancel out through interference. This explains why you can obstruct part of a mirror, and it still reflects almost normally. You're merely removing some of the arrows from the spiral ends. The central cluster near the minimum time path is what matters fundamentally. This is the connection between the photon picture and the principle of least duration, between particles and waves, between quantum mechanics and classical optics. Light selects all paths, but only paths near the minimum duration contribute significantly. Remember those pool waves? Different sizes? Light arrives in different wavelengths, and we assign them different names. The longest waves, meters to kilometers long, are radio waves. AM radio, FM radio, television broadcasts, all electromagnetic waves. Just extremely long ones. Shorter, centimeters to millimeters. Microwaves, radar. Shorter still, fractions of a millimeter, infrared, thermal radiation. What you sense from a hot stove. Then visible light, the tiny range our eyes detect, approximately 400 to 700 nanometers, 4 to 7/10,000ths of a millimeter. Blue is abbreviated, around 450 nanometers. Red is extended, around 650 nanometers. Shorter than blue, ultraviolet. What causes sunburn? Shortest still, X-rays, what doctors use to visualize your bones. Shortest of all, gamma rays from radioactive decay and cosmic events. All the same phenomenon fundamentally. Electromagnetic waves, oscillating electric and magnetic fields propagating through space. The only distinction is wavelength, is frequency. Different wavelengths, different properties. Radio waves pass through walls. Visible light doesn't. X-rays pass through flesh. Visible light doesn't. But it's all electromagnetic radiation. All electromagnetic radiation. All the same thing fundamentally. And it's all in this room at this moment. Radio signals from thousands of stations. Infrared from everything warm. Visible radiation bouncing around. Ultraviolet from the sun. Cosmic rays from distant galaxies. All the same category of waves. All coexisting. All passing through each other without interfering. A complete network of vibrating fields filling every point in space. So what is electromagnetic radiation? Not a wave. Not a particle. Light is light. We lack a word for it because we lack anything resembling it in everyday experience. It's a quantum object. When you're not observing, photons explore all paths, interfere with themselves. When you detect them, they arrive as discrete quanta, clicks in a detector. Both are genuine, both are true. There's no contradiction existing, just two aspects of the same quantum reality. We evolved to understand everyday objects, things we can hold. Light is none of those. Light is something else entirely. But we can understand it by following the mathematics and experiments. And they lead somewhere strange and beautiful. Think about what's occurring. Think right now. Photons from the sun, infrared radiation from everything warm, radio waves from hundreds of stations, X-rays from space, cosmic rays from distant stars, all passing through the same space at the same time. A tremendous disorder of waves. And yet, we can sort it out. Tune a radio and hear a single station. Observe and see a coherent image. Everyone understands electromagnetic waves fill space. But you must pause and contemplate it to genuinely experience the pleasure, the inconceivable nature of nature itself. When you understand what electromagnetic radiation is, really understand it, the world is far more strange than it appears, far more beautiful. And that's what physics is about, expanding our intuitions to grasp nature as it genuinely is. That's the beauty of it, the terrible, wonderful beauty of understanding.